Good morning, class. Let's start with the last subtopic for module 1, which is data transformation and discretization. So basically, data transformation is a function. There are four categories or four parts in data transformation: normalization, discretization, data compression, and sampling. So let's go on with data transformation first. Data transformation basically is a function that maps the entire set of values of a given attributes to a new set of values. Okay, it's trying to replace the existing value. So this ensures that each old value can be uniquely identified with one of the new values. Essentially, it's involving altering the data, make it more suitable for analysis or modeling. So there are a few methods that we can use to transform your data. The first one is smoothing. Smoothing, basically we try to remove the noise from your data. Okay, so it try to reduce fluctuations. It's techniques to reduce the fluctuation, makes the data more clean and more reliable for analysis. The second method is attribute or feature construction, where we try to create a new attributes or a new feature from the existing one. For example, by combining the existing features or deriving new metrics, so we can enhance the dataset's utility. Next, third one is aggregation, where we summarize the data and construct the data cubes. For example, this actually often done by grouping the data based on certain criteria. For example, like summing sales by region or averaging temperature by month. Okay, and the fourth method is normalization, where the purpose is to scale the data to fall within a smaller specified range. So there are few methods inside under the normalization here: minimum, maximum normalization, z-score normalization, and then the normalization by decimal scaling. Okay, and the last one is discretization, where it's a concept of hierarchy climbing. Okay, it's convert the continuous data into discrete intervals or categories. Okay, why do data transformation matters? Okay, it's improve the model performance. Okay, it enhance the interpretability of the data, and it is very efficient for your data analysis as well. Okay, so next one, normalization. Let's see some example for the normalization part. Okay, the minimum and maximum normalization, there's a formula you can see there. It's typically scale the data to a specified range from 0 to 1 or any desired interval from new minimum value to new maximum value. Okay, you can see here, new min A, comma new max A. So the V prime is actually the formula. Okay, so when we substitute, V is the original value over here. V is the original value. Minimum A divided by maximum minus minimum A. So you'll get a new maximum minus new minimum plus with new minimum A. So let the income range 12,000 to 98,000, normalized to 0.0 to 1.0. So then 73,000 is mapped to, so 73,600 minus 12,000 divided by 98,000 minus 12,000. Okay, you just need to substitute the value into your formula. 1 minus 0 plus 0 is equal to 0.76. So the minimum maximum normalization after you normalize the V prime that you obtain here is 0.716. Z-score normalization, we utilize mean standard deviation, where the z-score is the distance between the raw score and the population mean. In the unit of standard deviation, we have come across this formula before, right? Okay, so we let the mu is actually mean 54,000 and sigma is actually 16,000. So 73,600 minus 54 divided by 16,000, you will get 1.225. And the normalization by decimal scaling will be v prime is equal to v divided by 10 power of j, where j is the smallest integer such that the maximum will be less than 1. The v prime value will be less than 1. So this is how we do the normalization based on the formulas. On the other side, the discretization is a key technique to transform the data. So there are a few types there. Before we diving into the discretization, it's important to understand the 3 types of attributes: nominal attributes, ordinal attributes, and also the numeric attribute. Nominal values is actually values that come from an unordered set. Okay, example like color, profession, color like red, green, blue, profession, doctor, engineer. Okay, so ordinal attribute values comes from the ordered set. Okay, for example like military or academic rank. Okay, for example military rank will be private, corporal, sergeant. Academic rank will be like freshman, sophomore, junior, senior, and all these things. When it comes to numeric attribute, this will be a real numbers including integers and floating points numbers. Example, age, income, okay, temperatures, and so on. So what is basically discretization? Discretization is involved dividing the range of continuous attributes into intervals or bins. Okay, so the interval labels can then replace the actual data values, simplifying the data for the analysis. Okay, suppose we have a continuous attribute like age ranging from 0 to 100. Okay, just imagine we have a range from 0 to 100. How do we discretize the age into intervals? We have the set of range, right? Okay, 0 to 18, for example, is a child. 19 to 65 will be adult. Okay, 66 plus will be your seniors. So instead of using an exact ages, we can use this type of interval labels for analysis. This one basically we have learned during our statistics time. Okay, so the benefit of this discretization, basically by grouping continuous values into interval, we reduce the complexity and the size of the data set. Generally, that is the important part. Okay, supervised versus unsupervised discretization, where supervised discretization uses class information labels. We know that, for the class, supervised means we have a label to guide the discretization process. On the other side, unsupervised basically will be not use class information. Okay, and then we have split, top-down approach, bottom-up approach. Okay, and then we have a recursive discretization. So the applications of discretization will be in classification, okay, data visualization, and simplifications. Okay, data discretization methods. Okay, these are some methods that we still using till now. Binning method, histogram analysis, clustering analysis, decision tree, correlation. Correlation is very popular. Okay, in order to identify the variable correlation between variable 1, variable 2. Okay, let's see the first example, binning. So binning is basically consists of two category. One is equal width, another one is equal depth. So equal width is actually divides the range of continuous attributes into n interval equals size, creating a uniform grid. Okay, the formula for the interval width will be W equal to B minus A divided by N, where A is the lowest value, B is the highest value, N is the number of interval, and W is the width of each interval. So example, let's just fill up an example. For example, you have an attribute range from 0 to 100 and we want to create 5 equal width intervals. So N equal to 5. And your range is 0 to 100, which means A will be 0, B will be 100, and divide by total bins that you plan, 5, right? So 100 minus 0, divide by 5, you will get 20. So the interval range will be 0 to 20, 20 to 40, 40 to 60, 60 to 80, and 80 to 100. Okay, so this method is quite straightforward and to implement. Next will be equal depth frequency partitioning. This divides the n interval where the interval contains approximately the same number of samples. Instead of dividing by range, we divide by frequency, the number of samples. Okay, suppose we have 100 data points and we want to create 5 equal depth intervals, so n equal to 5. So each interval will contain approximately 20 samples, which means 100 divided by 5, you will get 20. The previous one, the width one, we have b minus a, which means 100 minus 0, right? But for depth case, we don't have zeros, so we just divide 100 divided by 5 equal to 20. So these intervals are determined based on the distribution of the data and not the range. Okay, they have their own advantages and disadvantages lah. You guys need to come across. I mean, when you apply these methods in your real analysis, you will get to know. Okay, binning methods for data smoothing. Let's see this one. Sorted the data for price in dollars. Just imagine the data is already sorted in increasing order: 4, 8, 9, 15, 21, 21, 24, 25, 26, 28, 29 and 34. Okay, so basically we try to partition into equal frequency. You can see here, okay, partition into equal frequency. When there is equal frequency, so how many samples are there? We have, from is taken 12 samples, right? 2, 4, 6, 8, 10, 12. So 12. So we want to have like equal bins, 3 bins. We will get 4 samples in each bin. Okay, so equal depth, that is what equal depth. And smoothing by bin, so this one by means. Okay, smoothing by bins means replace each value in the bin with the mean of that particular bin. Okay, you have to identify the mean for this, mean for this, mean for this. So each of the bin, they have their own mean. For example, 4 plus 8, 12 plus 9 is 21, 21 plus 15 is 36. 36 divided by 4, okay, 36 divided by 4, you will get 9. So the mean for this one is 9. So bin 1 is replaced with 9999. Okay, all the 4 values is replaced by 9. Bin 2, the mean is 23, so they replace with 23, 23, 23. And bin 3, the mean is 29, so they replace all the elements with 29, 29, 29. So this is smoothing by bin means. Now let's say we want to smoothing by boundaries. Okay, by boundaries means we replace each value in a bin with boundary values of that particular bin. For example, boundary values are 4 and 15, right? Which means the lowest value and the highest value, 15 and 4. So replace all the values in bin 1 with the lower boundary 4 except the last value, which is replaced with the upper boundary. Okay, so all the first 3 elements we replace 4, 4, 4. Last one we leave it to 15 because that is the nearest one, right? Okay, 4 to 9, which one is more nearest? So 4 is nearest, so they replace with 4. Compared to bin 15, bin 2 they replace with 21 to 25, so they replace 21, 21 and 25, 25. Okay, and last bin we have 26 and 34, so 3 elements become 26 and the last element remain 34. So this is how we do smoothing by bins. Again, these techniques help to reduce the noise, simplify the data for further analysis. So that concludes our sample of binning methods for data smoothing. So if you have, let's continue with the next one, discretization without supervision, without label. Okay, first of all, you need to understand the concept, the data. The first image shows the raw data, which is plotted in a scatter plot. Okay, the data is distributed across 2 dimensions, okay, x and y axis. There are 3 distinct colors, clusters. Is it 3 clusters? 4 clusters, right? I notice there are 4 clusters. Okay, and then this don't have any classes that we are performing unsupervised. So when it's come to equal width distance, okay, we have equal width, equal depth, and k-mean clustering. Okay, so each of these methods, so when the process is to divide the range into equal width interval, after that we have equal depth interval, divide the data into beam with contains approximately. So it doesn't mean that if you have it should have like 20, means it can be maximum 20, but you can have close to 20. Okay, and then the last one is k-mean clustering. We obtain this through natural grouping, where the cluster is represented by its centroid and the data points are assigned to the nearest centroid. Okay, discretization by classification and correlation. Okay, this one basically based on supervised. Okay, the previous one is unsupervised, and this one will be more towards supervised learning. So discretization by classification, the first one. This one is decision tree analysis, a common method used for this purpose. Okay, it's required the class label, as we know that. Okay, class label, we need a class label for this, and then the entropy based splitting, where the entropy is used to determine the optimal split point, the discretization point. And then the goal is to maximize the information gain and minimize the entropy at each split. This one also we already learned, right, during our decision tree time. I hope you guys can recall back. We have top-down recursive split as well. Okay, this process start with the entire data set, and then split the recursively split it into intervals based on attribute values. Okay, that provide this best separation of classes. On the other side, the correlation, like chi-square, okay, discretization, use statistical measure like chi-square to identify the best interval for the discretization. We have a bottom-up merge, recursive merge. Okay, but each of these methods, they have their own set of advantages, or the key points where we can apply. Okay, it depends on the situation, as I told you before. It depends on how your data set is fit into of the method, or else you need to modify the methods, or you have to come out with a different solution. Okay, next, concept of hierarchy generation. Okay, this one is actually organized concept hierarchically, where its associations with data warehouses, where the concept of hierarchy are typically associated with each dimension in a data warehouse. For example, like time dimension, year, quarter, month, and day. Geographic dimension, like we have a country, state, city, and neighborhood. Product dimension, we have a category, subcategory, product type, specific product. Okay, so this is how this hierarchy is working. Basically, it's like a hierarchy level. Level 1 is root. From the root, we have a branches. Each branch, they have a sub-branch, and so on. Okay. Next. Okay, for this one, concept hierarchy generation for nominal data. Okay, this one specifically for the nominal data, where the partial or total ordering at the schema level, where users or domain experts can explicitly define a hierarchy by specifying the partial or total ordering of attributes. For example, street, city, state, and country. So it's come from street first, then go to city, then go to state, then go to country. So this indicates that the street are grouped under cities, cities under states, and state under the country. So the specification of hierarchy of a set of values by explicitly data grouping, for example, Urbana, Champaign, Chicago, and Illinois under Illinois, for example. Okay, so these are some examples already given there. Okay, under the state, under city. Okay, for example, like we have like district, like under district Mua, we have like many places. Okay, under state of Johor, we have many district. Under district, we have many kampongs, for example, village. Okay, so something like that. Data compression. Data compression basically is a string compression involved reducing the size of textual data. Okay, text data. There are extensive theories and well-tuned algorithms for string compression. So this typically lossless. Okay, lossless means most string compression algorithms are lossless, meaning that original data can be perfectly restructured from the compression version and limited manipulation without expansion. While the compressed data is smaller, performing operations directly on the compressed data is often limited. So typically the data needs to be decompressed. Okay, decompress. Once you compress, you need to decompress again before you do any manipulation. Example algorithm like Huffman coding, LZW, okay, Lampel zip valve, and deflect are the commonly used for string compression in the format of such as zip file, gzip, and png file. Okay, audio compressions also there are possible, audio and video compression. Also again typically is a lossy. When it's come to a string, it's lossless, but when it's come to audio video, it's lossy. Most of the video audio compression algorithm are lossy, meaning some information will be discarded during the compression, but textual is not discarded. Okay, next, time sequence is not audio. Time sequences like sensor data, stock prices, weather data often exhibit patterns that can be exploited for compression. So the key characteristics are short and slowly varying. So the time sequences are typically short and change gradually over time, so making them amenable to compression techniques that exploit temporal redundancy. So example, sensor data from IoT devices often generates large volumes of time series data. So the compression techniques can reduce storage requirements while preserving the essential trends and the pattern. So basically the trend and the patterns of the data are still there, but it's try to reduce the data because time series data is generated like, every milliseconds, how they set up the parameters. So what is lossy and lossless compression? Lossless compression preserves all the original data. On the other side, lossy compression discards some of the data to achieve higher compression ratio, which means some is lost, some is lossless. I mean the data. Okay. Next is data cube aggregation. Data cube aggregation is the base cuboid represents the most detailed level of, you can see the base detail level of data in the data cube. So each data cube represents something. The characteristics, it contains the aggregated data for individual entity of interest. For example, in a phone calling data warehouse, the base cuboid might represent data for a single customer. For example, consider a data cube that stores call records. The base cuboid could contain details such as customer ID, call duration, call time, call type, local or international. Okay, this level provides the finest granularity of data, capturing specific attributes of each entity. Next, multiple level aggregation in data cubes. Okay, it's to reduce the size of data and enable faster querying at different levels of detail. The process, basically higher level of aggregation, are created by summarizing data from lower level. Okay, so example, the data cube might have the following aggregation level. For example, like level 1, base cuboid, individual call records for each customer. Level 2, total calls per customer day. Level 3, total calls per customer per month. And level 4, total calls per region per month. So the classification and the categorization of the customers, okay, that is the each cuboid function in the warehouse here. Next is reference appropriate level. This use the smallest representation of data that is sufficient to solve the task. Okay, why? Because using higher level aggregation when possible reduces the computational overhead and improve the query performance. Example, if a user wants to know the total number of calls made by a customer, by all customers in a region for a given month, querying the monthly aggregation level is more efficient than summing up individual call records. So they want all the customers, not one particular customer, and from one particular region for one particular month. So which means they can identify all the customers from the region, same region and the same month. Queries regarding aggregated information, it's when possible answer queries using pre-aggregated data from the data cube. Example, instead of calculating the total sales for a product category across all the stores, use the pre-computed aggregate stored in the data queue. Okay, next is automatic hierarchy generation. Okay. Some concept hierarchies can be automatically generated based on the analysis of the number of distinct values per attribute. Okay, the attribute with the most distinct values is placed at the lowest level of hierarchy exceptions. Example, okay, let's see an example over here with weekday, month, quarter and year. So for example, country, we have a 15 distinct values. Inside country, we have a states, 365 distinct values. Inside a state, we have a city where we have 3,567 distinct values. And the street inside a city, under a city, we have like 674k distinct values. So this is how we have the automatic concept hierarchy generation. Next is the sampling. Okay, I guess if you learn statistics, you would have come across about sampling techniques. But this one may be slightly different or maybe very basic level. Sampling basically involves obtaining a small sample S that represent the whole data set N. Okay, why sample? Large data set can be computationally expensive process. So sampling allows us to run mining algorithms with potentially sublinear complexity relative to the size of the data. Okay, so still there are limitations and advantages with this. So we have a few types of sampling methods. We have stratified sampling. We have simple sampling method. Okay, so you guys can check on this. Okay, let's see here. Simple random sampling. Next, simple one is every possible sample of a given size has an equal chance of being chosen. Okay, on the other side we have sampling without replacement. Okay, this one prevents the duplication in the sample. So once an object is selected, it is removed from the population. Okay, and sampling with replacement, this one is simpler to implement in some cases. It's useful when the population size is very large or infinite, like continuous process. Okay, and lastly we have a stratified sampling where it's divide the population into distinct subgroups, strata, and then sample from each stratum proportionally. So it's ensure that the important subgroups are adequately represented in the sample. So we didn't miss out the significant samples from the population for the analysis part. Okay, I guess that's all for the module 1. So we have covered 1.1 until 1.6, all the basic to the advanced level of data pre-processing. Whatever things that we learned during our fundamental data science time is very basic data preparation and pre-processing. Okay, so here I guess I would have teach you the more detailed, more breadth and depth of data pre-processing with some of the techniques. Okay, after this lectures, I will give you some practical hands-on video as well, so you guys can try. Then we will have some quiz and assignment and also final assessment for module 1. Thank you.